Okay, so we're going to look at a thing called stratification. So let's go over to the slides and start thinking about what this means. So occasionally we will be using logistic regression, and we have some response variables, some success or failure, and we'll have some treatment, and we want to see if there's an association between the treatment and the success or failure. But it might be that we have done this over numerous and some sort of extra blocking variable, some other variable. So we repeated this experiment where we're looking at the association between success and failure and some treatment, but in lots and lots of various other, I suppose I could call it another treatment or blocking variable, it's sometimes called, what we're going to call strata. So let's think about a classic example to sort of do this. So this is actually a data set, a famous data set. In the 60s, there was word that there was sexism in the admission in UC Berkeley, and it actually got analysed to see if there was. So it was an observational study. So they looked, and what they were looking at is they were looking at, in this case, success or failure. Success was you were admitted to a particular department. Failure was that you failed to get admitted. And the treatment in this case was gender. They wanted to know, to some extent, was there an association between your gender and the probability that you would be admitted into UC Berkeley? So what we've got, the information we've got is for each applicant, we know whether they were admitted or not. We know the sex or the gender of the applicant, and we also know which department they applied to. So in this case, the response variable is success, admitted, failure, not admitted. The treatment is gender, male or female, but we also have this extra strata, this thing, department. We don't really care about the effect of department, but we want to take it into account, and you see that it's important to take it into account in our analysis. So our department is going to be our strata. So there we are, just exactly what I said in this context. Sex is the treatment variable, admission is the response variable, and department can be thought of as defining strata. So let's quickly have a look at a contingency table. So what I've done here is I've summarized. So each row is the level of our treatment. So we've got female and male. I put female first because first alphabetically, that all classes are level 1 and male are level 2. And then we've got our admitted and our rejected. And what we've got here is we see that we have 557 females who were admitted into the departments in UC Berkeley, and 1,278 rejected. So only 30% of the females were admitted. Now, if we look at males, we get about 45%. So initially, looking at this data, it looks like there is some sort of sexism going on, some sort of structural sexism that says that males are more likely to be admitted into UC Berkeley than females. Okay, well, we've got this extra information about department. Why don't we find out which department is being sexist? This is where it gets interesting, because in department A, and I've just called them A, B, C up to F, but in A, we see that in this case, the success rate for females was 0.82 and males only 0.62. So A is actually sexist, but it's to some extent, towards females. It's accepting more females. Well, B is more females. Okay, this is strange. C, yes, there's a little bit of difference, but they're really close. There's not a lot of sexism. Again, D, females. E, again, a little bit towards the males, but not a lot. And F. So the thing is, when we pull the data together, we saw definitely seems to be much more likely to be admitted if you're male compared with female. But if we look at each individual department now, there isn't one that, in fact, they're all the wrong way round. There's something going on here. When we look at individual departments, in the individual strata, we see that there can be a significant difference between male and female, but often towards the female. The females are more likely to be admitted. So what's happening? So let's set up a model. The way we're going to actually look at this, we're going to look at what we call the odds ratio. So we'll go back to this contingency table. I've got my female, male, I've got my admitted, rejected, and I've broke it down for department I. Yeah? And what we're going to do is we're going to let pi ij be the probability of admission for sex j, and as I said, female will say j equals 1 and male j equals 2 in department I. So what we're going to do is we know we can calculate the odds. So this top bit here is the odds of being admitted if you're male, because it's the probability of being admitted to department I if you're male, over 1 minus that. So that's the odds for males. This is the odds for females. We're going to take the ratio and take the log, and we call this the log odds ratio. And we can use that as a measure of association between sex and administration. So how do we interpret beta I? Well, basically, if it's greater than 0, admission is more likely for males. If it's less than 0, admission is more likely to females. And if it's about 0, it's equally likely for males and females. So here's a nice example to illustrate. So this is for Department A. So all I've done is I've gone and looked at these numbers here. So first of all here we've got it's pi 11, which is the first department, females. We've got 89 admitted out of a total of 89 plus 19. So we've got a P11 of 0.82. For male P12, we've got 512 admitted out of 512, 313. So our P22 is 0.6. So in this case, you can see that females are more likely to be admitted than males. If we calculate our beta 1, which is our log odds ratio for Department 1, we get a negative. So in this case, females are more likely to be admitted. So now we're going to set up a model. We're going to set up a model that says, we're going to say the logit of our pi ij, which we're going to fit, we're going to have an overall, our intercept, plus a level for the individual department, plus a level for the gender. Okay? The interesting thing is, now if you look at this, if you look at each individual department and substitute in, you see that the thing that only matters is B2 minus B1. There is no effect. You can see there's no I here. The I's disappear. The way we set this model up is that we find that the odds ratio for every department will be the same. The odds ratio. So it's what we call a common odds ratio model. Mainly because we don't have an interaction term in here. We don't actually have enough data, but if we could put an interaction term in, and then we could actually have different odds ratios. So what this is going to do, it's going to combine all the stuff together. But it still does take into account, you can see we've got that department term there. And if you do that, and we will be doing this case study, you'll actually see me do the analysis in R, you'll see that the common log odds ratio is minus 0.09987. Remember, if this is close enough to 0, we'll say there's no difference between male and female. And with this standard error, we find it's not significantly different from 0. So what that's saying is, there is no strong evidence of discrimination within departments in either direction. So we've got a model that has department in there, it has gender in there. You can't have a sort of different odds ratio for each department, but you can put this information together and says there is no indication, once you take into account department and gender, of any sexual or sexism in there. But we saw that thing where we go, well, why don't we remove the department effects? Why don't we actually remove them and just have a model now that has an intercept plus a gender level? So this is the equivalent to that very first table. And we looked at that very first table and said, let's just have a look at that. Now we find that there is sexism. And in fact, it's positive and a strong bias towards male applicants. And this is what we call Simpson's paradox. Because it seems paradoxical. If you think about it, if I take into account the department, there is no sexism. There is no bias towards either gender. If I ignore department and put all the data together in this very simple model, now we get bias towards male applicants. And you saw that before. You saw the fact that in each individual department, sometimes they were biased towards females, sometimes males, but generally not too bad. But as soon as you put them together, we got this bias towards males. So what's happening here? Well, I want to try and illustrate this with a diagram. It is a paradox. It's non-intuitive, but let me see if I can illustrate it. So what I've got here, on the x-axis, we've got female and male. And the lines join departments. So, for example, if you go to the top one here, with this department, you can see this on the y-axis is the proportion admitted. So we've got about 82 of females who admitted to this department and only about 62. So anytime that the point on the left is higher than the point on the right, they favour females. Well, if the point on, and I can't find one this one here, you can see in this one they favour males. And what we're finding is generally they're about the same level, or they drop down. They are favouring females compared with males. But when we put the data together, this is indicated by this black line. You see that here, the proportion of admitted for females is about 30%, while for males it's up about 45%. So why is this happening? What's actually happening? Well, let's look at another thing now. What I've got here is I have dots, which basically I've plotted for each, all the departments, all the females. I've plotted the proportion that were admitted and how many applied. And the colour indicates whether we're looking at females or males. And what we see now, if I just quickly put a line on that, a linear regression on that, the problem we've got is you can see that when it looks at departments that admit a lot more, a lot less females are applying. Well, if we go down to the ones that are admitting less, so this is a department that doesn't admit very much, there is more females applying. Well, males are the other way. The males, what they're doing is the departments that will admit more, they're going for. And you can see this separation line is what's explaining that problem. What's happening is, in any individual department, females are more likely to some extent, or about the same, to be admitted as males. But the females are applying to departments that are really hard to get into. So the males look better because they're going to departments that admit a lot more people, and so they get a lot more males admitted in that. And that's the main problem we see in this data. And that's why you get this Simpson's paradox. So to repeat that, when you look at the individual departments and look at how, sort of how many people they let in, what proportion they let in, females apply to these ones less than the harder ones to get into, while males are applying in more numbers to the ones that are easier to get into. And so overall, males end up succeeding a lot more. Okay, so we'll stop there and we'll repeat this and we'll actually go and look at this data in our case study at the end of the week. And next lecture, we'll look at prospective and retrospective studies. See you next time.